We're going to have a lecture today for about an hour or so about looking at dimensionality, how to measure things out in space. Because that's one of the things we want to do. We want to look at different things out in space and see how big they are, how small they are. And so we're going to start off with thinking about how I measure things like distances. So we'll start off with a distance. How do I measure a distance? What do I need? What pieces of information do I need to measure the distance? Yeah? What am I going to, what would I use with the measurement? What do you mean by measurement? Yeah?
You need like a starting point and ending point?
We want a starting point and an ending point. Right? So you have start and you have end. And when I measure a distance between these 2 points, right, I use some units. We've talked about units a little bit before. So what's a unit I could use to measure a distance?
Kilometers?
Kilometers is one idea. Kilometer. Does anyone recall what kilo means? 1,000. And meter we can abbreviate as lowercase m. And that's another way of talking about it. This is a way to measure length. So what we're trying to measure here is length. From one point to another point. Right? And I hope everyone is sort of comfortable and familiar with how this works. Measuring length from one point to another point. Our base unit for measuring length and distances is this meter, this idea of meter. But we're going to come up with some other units as time goes on that may be interesting too. But we'll start with meters, then we can move on to other units by adding these prefixes like kilo, mega, centi, deci. All these other prefixes have numbers. The number multiplies by the unit and it tells me how big or small I'm looking at. What part of the scale I'm dealing with. Okay, so this is the first idea of distance, but there's lots of ways to think about distance and lengths. So one way is just to have a start and an ending point, but there's also a particularly interesting kind of shape that we're going to look at and see quite a bit in this class, and that's this shape, the circle. Are there lengths to measure, distances to measure on the circle? What would we measure here on the circle?
Circumference.
So we could measure the circumference, which is all the way around, and that's often what we're interested in. Because we'll find that things tend to go in circles and we want to know how far they went. In that case, it's a little bit interesting because your starting and your ending point are the same place. But if you can imagine sort of keeping track of how far you went around the circle, you could measure something called the circumference. So we try to figure out how we could do that. Maybe you get a long string and you can wrap it all the way around and then figure how many meters, how many kilometers, whatever unit you most like that is. That's one way of measuring a circle. There's other distances in here on the circle. Yeah?
Could we try the radius?
There's something called a radius. So what's the definition of a radius?
From the center to...
The radius is a distance, this is a definition, from where to where? A to B.
Center to the...
From center to what?
Any points on the side.
To the outside. Right? Or to the border, we might say. Now, I could have said any point on the circle, but the fact is that I'm going to see radii in things that are not circles, that are other things as well. And this always holds. It's always from the center to the point where it just goes to the outside. That's what we would call a radius. So I need to find a center of my circle, and then I'm going to go out to the edge, and I call that the radius. Now, you may have learned in math class that you could do twice the radius and call it the diameter, but we don't need that. We just need radius. The plural of radius is radii, so we're going to talk about radii. And occasionally we'll want to do circumference. Does anyone know what the relationship between a circumference and a radius is for a circle? Yeah.
Since the circumference is directly like half of the circle and the radius is, no, yeah, I mean circumference is directly like the circle cut in half and then the radius is like half of that.
Well, you're talking about half of a diameter, right? So the diameter is halfway across. But I'm talking about going all the way around. Is there a relationship between this distance and this distance?
Isn't like the radius, I think, a quarter of the circumference?
Well, not exactly. It's close. We'll actually figure out exactly, but it's a fraction. You can see that the radius is certainly smaller than the circumference. The question is, could you multiply some number times the radius and get all the way around, get the same thing? And the answer is yes, you can. Yeah.
So you need the radius.
So you do have the radius. We're going to assume we have the radius.
So it would be pi r squared?
Not pi r squared. The reason I know it's not squared is we'll get to the idea of dimensions. That's multiplying the radius by itself.
2 pi r?
Okay. It's 2 pi r. So a circumference for a circle is equal to 2 times this peculiar number, pi, that's one of my favorite numbers, times the radius. Right? In some ways, we could say that that's the definition of a circumference. We'll often be given the radius, and we'll need to figure out what the circumference is. Occasionally, you'll have a circumference, and you want to find the radius, and we can talk about how you would do that. But this is a fact you may have come across in math class before. If you take the radius of a circle, and you multiply it by 2, and you multiply it again by pi, you're going to get this circumference. In this class, we are just trying to get approximate measurements here. We don't care about very accurate measurements. We care about getting the sort of scale right. If you talk about scientific notation, we're interested in getting that exponent, that little number above the 10 rate. So in this class, we want to think about whether we want to take consideration of the full glory of pi. Pi, if you look it up, actually has an infinite number of digits. It never ends. And there's no pattern to it. There's nothing that you can do to sort of work out what the next digit is by looking at the previous digits and trying to come up with a pattern. But in this class, we don't have to worry about all those little bits that you may have worried about in math class. In this class, the following thing we can say is fine. That pi is basically 3. And you can always do that. Always, always, always. If you ever see a pi show up, you can always replace it with 3 and you're going to be okay. So that's what we're going to do here. We're going to say that we have a circumference. We're going to get a little bit bogged down if we have to keep writing circumference. So I'm going to use the letter C for circumference, if that's okay. And I'm going to say, all right, in this class, we can say pi equals 3. So we'll start with the circumference C. And we'll say C is equal, it's approximately equal, so I use this sort of wavy equals to mean approximately. 2 times what? 3 times, now we'll call the radius r. Right? So here's my circumference C, and here's my radius r. Well, what's 2 times 3?
6.
6. So we can say approximately that if I take the radius and I multiply by about 6, I'm going to get the circumference. So whoever said it was about a quarter, you were off a little bit. It's not too bad, but it's actually 1/6. The radius is 1/6 the way around, approximately. Not exactly. If you want to go exactly, you can't use this approximation. But we don't need to be exact. We just need to get a sort of general idea, and that 6 is what we'll tend to use. So if you're ever going to be calculating how far I need to go, and you know a radius, but you don't know how far around you're going to go, you just take that radius and you multiply by 6, and you get an approximate, a good guess as to how far you're going to be traveling around in a circle. Okay, so that's the first thing I want to do. We're going to deal with some other shapes that are based on circles as well. But I wanted to make sure that we were clear about this, how you're going to calculate circles. And that's as simple as that. We have the idea of a radius. If you ever need to get a circumference, multiply that radius by 6. If you have a circumference and you need to get a radius, what do? If you know how far around you've gone in a circle, and you want to know how far it is from the center to the outside, what do?
Divide by 6.
Divide by 6, right? As simple as that. If I take this and I solve for r, I get that c divided by 6 is r. Yeah. Is that okay? Everyone follow what we're saying here? So that's the first thing I wanted to talk about with respect to distance. The next thing I wanted to talk about is the idea of speed. What is speed? How fast something is going. So how would I come up with a speed? How am I going to figure it out? What the speed is.
Distance times time.
It certainly involves a distance, right? The further I go, sort of in a certain speed, the more time it's going to take.
Distance over time.
So distance over time is actually a definition of speed. So we've already talked about distances. You can imagine that you could measure the speed of something going around in a circle, because you would know how far away it went around. You can do the radius, for example. And maybe you could figure out how long it took. And I would get a speed of something moving in a circle. But we're going to just start off like this with speed in general is going to be a distance divided by a time. This is something that you're going to end up calculating a lot in this class. You're going to end up calculating speeds or distances divided by time. And there's a special speed we use quite a bit. Anyone know what that speed is?
Meters per second.
So that's a unit, right? We can talk about the units that we measure speed in. We can talk about the idea that we're measuring lengths in meters, and we might measure times in seconds. But there is a very particular speed. If I time something that's going a certain distance, and it's always the same type of thing, it always moves at one particular speed. Does anyone know what this is?
Velocity.
The velocity is a sort of another name for speed. What's the thing that always moves in the same speed? There's only one thing in the universe that always moves the same speed. Light. So light speed is something we're going to use a lot. And there's a lot of ways to express what light speed is. One way to express light speed is to say that it's equal, usually use the letter c, to 3 times 10 to the 8. And as was pointed out, a convenient unit for speeds is a distance, meters, divided by a time, seconds. This is one way you might write that. Another way you could write this, and it's exactly equivalent, is that it's 3 times 10 to the 5 kilometers per second. Those are equivalent. Or you could write that it's equal to 3 times 10 to the 10 centimeters per second. Again, equivalent. So we're coming up with a lot of different ways to express light speed. But sometimes you don't want to decide what units you want to use right away. In that case, you might use this c, and we should distinguish here. Here we use sort of like a capital C for circumference. Over here, this is typically a lowercase c, a little c. So we can start with these little c's, and you might find that if you need to keep in mind the speed of light, you'll just keep track of it by just saying c, and at some point towards the end, you'll decide what way you want to measure it. Do I want to measure it in kilometers per second, meters per second, centimeters per second? We'll actually come up with some other units as well. An interesting unit to consider is something called a light unit. Light units are actually units of distance. How does this work? Well, I look at my definition of speed and I can rearrange it. What if I multiply both sides of this definition by time? What would I get? If I multiply this side by time, I would get speed times time, right? What if I multiply the other side by time? What do I get again?
Speed over time.
Distance divided by time times time, what's going to happen?
Distance.
I'm just going to get distance. The times will cancel, right? As long as I'm using the same time, which I am, they'll cancel. All right, so I can say that this statement up here is the same as this statement down here. This is just a simple way of using algebra to come up with a different True statement, different way to talk about things. If I wanted to describe a distance, one way to describe it is it's a speed times a time. And I know that has to be true because that's the definition of speed. Well, one speed I could choose would be the speed of light. So what if I chose the speed of light? I'm going to choose, this is a special choice. Special choice. I'm going to choose a special choice of the speed equaling to c. I'm going to multiply that c times some time. And when I do that, I'm going to get out a distance. Well, what times could I choose? Let's name some times that are possible.
Eastern Standard?
Well, that's a time zone. But if I'm going to measure time, what do I measure it in?
Hours.
Okay, so we have a lot of different ones. Let's try hours. Right? So what if I took c and multiplied it by an hour? What do I get? Well, there's a lot of ways to talk about it, but the simplest thing to do is I just take that c, I say that's light, hour. That's a distance. Now, what if I wanted to know what that distance was in a different set of units? I could figure out how to do that. How would I do that? Well, what unit of measurement would you like to know how long a light hour is?
Seconds.
Well, light hour is not a measurement of time, it's a measurement of distance. So you can choose meters, kilometers, centimeters. Which one would you like to choose?
Kilometers.
Kilometers? Would that be something you'd like? Okay, let's try that. So if I wanted to know how many kilometers was a light hour, what would I do? Well, I take the speed that would give me kilometers. Here it is. 3 times 10 to the 5. Kilometers per second. And I'm going to multiply this by an hour. Okay? Multiply that by 1 hour. Nothing looks like it's going to cancel quite yet. So what I need is something called a conversion factor. If you look at the previous lecture, we talk a lot about how conversion factors work. But there's a way to convert between hours and what's the other unit of time I see here?
Milliseconds.
Seconds. How many seconds are in an hour? Does anyone know?
360.
More than that.
3,600.
It's 3,600. It's 60 times 60 because there are 60 seconds in a minute and 60 minutes in an hour. So 3,600 seconds is the same thing as 1 hour. So I could just take this and substitute. That's one way of talking about this. If you go back to the previous lecture, the lecture number 2, the way we often deal with this is we multiply by interesting factors of 1. I rewrite this statement to look like this. 1 is equal to 3,600 seconds divided by an hour. And if that's confusing to you how that works, go back and watch that lecture. But 1 is equal to 3,600 seconds divided by an hour, so I can actually write that here. 3,600 seconds, lowercase s is always seconds, divided by 1 hour. Now, what's going to happen here? Hours will cancel. What else will cancel?
Seconds.
Seconds. Notice the second is down here, and the second's up here. So now it becomes a simple math problem. It's this number times this unit times this number. All right, well, let's see if we can do that. In fact, we can do this without a calculator. How do I do this without a calculator? I say this is 3 times 10 to the 5. I'm going to put all my units at the end, so it's going to be kilometers at the end. I don't want to forget that. But now I have this other number, 3,600. There's a way I can write this in scientific notation. 3.6 times 10 to the, how many? 3, exactly. So if that's confusing, go back and look up and try to see how that's done. But I can write it like this. Now the advantage here is now I can start to group all of my 10s together to the power and all of my other numbers. So when I group my 10 to the power together, there's a nice thing that happens. When I multiply 10 to the 5 times 10 to the 3, in order to figure out what that answer is, all I have to do is what to the exponents? Add them together. So what's 5 plus 3? 8. So I have 10 to the 8 as all of my 10s. I could even cross them out and keep track. And then I have 3 times 3.6. Now, I don't have to be exact here. So let's estimate what 3 times 3.6 is. What's 3 times 3? 9. What's 4 times 3? 12. So I know it's going to be between 9 and 12. Is there a nice number between 9 and 12? There's a pretty great one. 10, right? I'm going to estimate it as a 10. Is it exactly 10? No. But in the same way I said pi equals to 3, 3 times 3.6. In this class, I might as well estimate it to be 10. So I have 10 times 10 to the 8 kilometers. What's 10 times 10 to the 8? 10 to the 9. 1 billion kilometers. That is how far a light hour is. I went very slowly through that derivation, but that derivation will work for any unit. Remember, it's a special choice of distance. So I take the speed of light and I multiply by any time. I can multiply by hours. I can multiply by seconds. I can multiply by years. A light year, in fact, is a calculation that I've already done in the previous example. If you go in to see the previous lectures, you can see I calculated how long a light year is. Now I've calculated how long a light hour is. So light units are extremely important. We'll use them a lot. There's a homework question that asks you to calculate certain scales in light units and try to compare to some sizes that might be out there in the universe. And that's something that you'll need to do. And to do that, one way to think about it is I take the speed of light and I multiply by whatever time. So if I said light millennium, I take the speed of light and I multiply by 1,000 years.